but there are a lot of them out there. So some of them are bigger than Pluto, so I'm sorry Pluto ignore it, but it's okay. You have many friends. So now I'm going to take a few minutes to talk about the new telescope we're working on, the James Webb Space Telescope, because it will help work on this question of how did the planets get here, how did we get here. I mentioned earlier that we want to study infrared for a number of different reasons. One that I told you about is that the infrared light will pass through or around the dust grains that obscure our view of the stars that have just been formed. Another one is that, of course, infrared is the place to look for the early universe. But I thought, well, we'll concentrate on planets today. Another one is that infrared comes from things at room temperature. Things like us. If you want to study Earth-like planets, let's study the wavelengths at which they exist and for which they emit. So here we are, friends of ours, allowing their pictures to be used. But at any rate, so infrared tells us different things. So what's the new telescope look like? This is the James Webb Space Telescope. It does not look like any telescope we've ever flown. What you see here is more like a solar energy concentrator behind a shield. So it's a galaxy energy concentrator. So light comes from the lower right in this picture, bounces off that hexagonal mirror, and is focused onto this mirror, which is at the end of the triangular tower, and then bounces back into the instrument package there. This is all going to be operated at Lagrange point L2, which is pretty far from Earth, but not nearly as far as Mars. It's 1 million miles away. I'll show you where that goes. The long grayish thing that you see there is actually an umbrella, and it has 5 layers, and I'll show you how it unfolds. This telescope looks like this partly because it's bigger than the rocket. So this is the first time we're trying to put up a giant deployable telescope into space and make it function in the way that it should as a proper telescope. It's a partnership doing this project. NASA is leading the partnership, but we have big contributions from Europe and Canada, including that Europe is supplying the commercial launch vehicle, the Ariane 5, to carry the payload out there. So, I'm not going to be able to tell you the whole story about what we want to do with this, but I'll show you where the telescope goes. Here's the diagram of the Lagrange points. Many of you have heard about L4 and L5 because they're stable places in the orbit. On the other hand, they're pretty far away. Each of them is 1 astronomical unit from here. We actually like this little L2 point, which is overhead at midnight for us. It's 1 million miles away, so it's about 4 times as far away as the moon. And it's an unstable orbit point. We have to keep nudging the spacecraft to stay there, but that doesn't take much of a nudge to do it. So here's how big is the telescope. This model is made of steel. This is not the real one, but here it is on the lawn over at Goddard Space Flight Center. And this is about 1/10 of the worldwide engineering team and science team that's working on this mission. It's a very large collaboration to do this. People might say that it takes a village to build a telescope. So I'll show you how it's supposed to unfold. I mentioned that this is much larger than the rocket can be. On the other hand, eventually maybe we'll get bigger rockets. So here is how it unfolds. This is about 10,000 times faster than it can go. First we unfolded the solar panels and the introductory dish. Now have erected the telescope on its tower and we're about to unfold this the sun shield. Now in real life, the sun and the Earth will be below this observatory so that the telescope that you see there will be protected completely from the heat of the sun. And it will be able to cool itself down by radiation to outer space down to about 20 degrees. So this is what it takes to do an infrared telescope in space that's far more powerful than the Hubble. We did look, by the way, to see if it was possible to put this telescope close to Earth, and we could never find a way to do it. The Earth is too warm. So here you see now there are 5 layers of that sun shield. That's what it takes to protect it well. It's a sun protection factor of about 1 million for your sun rocket. So there's the telescope more or less set up. It will be adjusted after launch to be the right shape. We did learn from Hubble how to adjust a mirror. We got math. So the mathematics we had to invent for the Hubble are exactly the same we're using to do the fine adjustment for this telescope so that that collection of 18 beryllium hexagons will function as one single giant parabolic mirror. You might say, well, that's kind of hard to do. How can you imagine doing that? And you know, this is a tremendous challenge for mechanical teams. So how are we going to make sure this works? Well, clearly we are going to rehearse a lot. We're going to do a lot of testing. We have people at the company that's building this, which is Northrop Grumman, and they work for other government agencies, and they cannot tell you what they do, but they tell us that this is definitely not the most complicated thing they've ever put up. So people are watching you. It's good. So I'll just illustrate one thing we are going to do. I can tell you more about this one. This is the optical test we're going to do. Now, the Apollo astronauts rehearsed their trip to the moon using this giant vacuum tank in Houston, and we find that it's just the right size and shape for our test. We're going to wheel in the telescope on the track there, and we're going to put the instrumentation up at the top. It turns out the center of curvature of the instrumentation at the top, so it's the right size and shape. This will soon become the world's largest helium-cooled tank. We have to make the whole inside of that apparatus come down to near 20 Kelvin so that we can test the telescope at its operating temperature of about 40. So this will be a pretty amazing project. And it will be launched according to plan, as mentioned, in 2014. Now I'd like to wrap up with a few speculations about what might come next so we can think about those planets around other stars. Here is a sketch of an idea called New Worlds Observer. This is a way of seeing planets around other stars. It's quite different from the ways that we've tried before. You would say, well, can't we just point a telescope at the star and look for the planet next to it? And the answer is, well, yes, you can try, but there's an awful lot of glare in your telescope. The Earth, as seen from a great distance, is 10 billion times fainter than the Sun. And that's an awful lot of contrast. So you have to have, if you're going to see the Earth next to the Sun at a great distance, you have to get rid of almost all of that sunlight, and where are you going to put it? So here's an idea. This is called an occulter, and the idea is to put up this thing that looks like a pointy sunflower, but quite large, about 50,000 kilometers away from the telescope. Well, 50,000 kilometers, that's a small amount in this business of space. So if you can do this, and you can cast a shadow of the star on the telescope, and the shadow will be big enough to put the telescope in, but nevertheless, the planet that you're hunting for will be off to the side a little bit, so you should be able to look around the edge of this star shield and see the planet Earth, or Earth-like planet out there. So this is an idea. We studied it quite a lot over the last few years, and my colleagues say that they could build it. So will we build it? That's a whole other subject. This is not easy, because this shield that's up there, that has to be something like 50 meters across. So we have not built something that large with the kind of precision that's required. This one has 4 telescopes in a row, all collecting light from the star at infrared wavelengths and sending them over to the little combiner device. It's a 5th observatory, flying information with these others. So this one, also difficult, but I guess what I'd like to point out here is if you could build this one, there's a possibility you could see the signs of life in the atmosphere of another planet this way. The little graph there shows you what the infrared spectrum of such an Earth-like planet would be from a distance. There are 3 compounds noted there. There's water, ozone, and carbon dioxide. And that's because that's what Earth looks like. Well, the ozone is there because we have plants. And our job here on Earth is to make carbon dioxide for them. So anyway, from a distance, we can make an observation that would tell us if a planet is like Earth because it's alive like Earth. It wouldn't tell you that there are people over there, but it would tell you that there are plants over there.